All right, hopefully at this point you've gone through the warm-up. Here is the work that should have happened. Keep in mind we're using the formulas that we've used the past few days. So here we had AN equals 14. So this is our A1 minus the difference times n minus 1. So we got that 60 or 20 minus 6n. So if we're taking the summation of 20 minus 6k, remember from the last time we talked, we have A1 plus the last term. So for the last term, we've got AN, and then you're multiplying that by however many terms there are divided by 2. So n divided by 2. So that's how we ended up with the negative 90. We found that negative 34 by finding the 9th term. So the 9th term should be our nth term. So that's how we found that negative 34. We just plugged in 9 for the k here. Good. And then for the second one, it was geometric. So hopefully you use that geometric series we found last class. So starting off, we just found AN. So we've got the A1 and the rate, our common ratio. Then we put it together with the summation. And then remember last class that geometric series that we found was A1 times 1 minus r to the n, all divided by 1 minus r. So that is what is occurring down here. So by plugging in that negative 1/2 for our r's and 11, which was how far we wanted it to go, for n, we ended up with the 4.002. 1 second. All right, I fixed the screen. So next part, we've learned that sequences can either converge to a number or diverge to infinity. So if we were graphing a sequence that converges to 3, that could look something like, if this is 3, if it's converging to 3, remember we pointed out last class that if it's a sequence, those are not continuous points. So it's going to be those random points that you're adding up should go towards 3. If we had a situation like that, that could be a series that looked like AN equals 3n plus 2 over n. If you remember anything from graphing with asymptotes, here we've got the degree is the same on the top as on the bottom. So that should have an asymptote at the leading coefficients divided by each other. So our horizontal asymptote here is 3 because this is n to the 1, n to the 1. So 3 is my leading coefficient, so we're converging to 3. Oh, it is not letting me scroll down. There we go. All right, if it's converging to 0, same situation, except this time, instead of our points converging to 3, we're converging to 0. If we label these, our x-axis should be n, and our y-axis should be an. In this situation, an should equal, or could equal something like 2n plus 1 over n squared. Or it could look like an equals 1 over 3 to the n power. So what we're looking for here is that the bottom is getting bigger faster than the top. Because remember from graphing with asymptotes, if the degree is greater on the top or greater on the bottom, then your horizontal asymptote should be 0. So in this situation, we've got n squared is below n, so we know the bottom's getting bigger faster, so it's going to go to 0. In this situation, you'd end up with 1 over 3n. So the bottom is also getting larger faster, so it's going to go to 0 as well. Finally, graphing a sequence that diverges, that could be anything that's not converging to 0. So one example could look like points making a line going up. So it could be linear, There's a lot of different options for diverging. But one possibility could look like 3n plus 2. And that would be a sequence that is diverging. So now, considering those three series, will they converge or diverge as you add more terms? So now we're getting bigger and bigger. So we're not just looking, the last slide had sequences. Now we're thinking about them like series. So the series means we're going to add up all the terms. So for A, if we took the summation from n equals 1 to infinity of that 3n plus 2 over n, if we started plugging in numbers for n, so we start with 1 and get 5, then plug in 2 and get 4, plug in 3, plug in 4, etc. Keep adding. It's going to keep getting closer and closer to 3. But if I keep adding these up, my number that I'm getting when I add them up isn't 3. It's getting huge. So in this situation, if you add it up, it's going to diverge. So the series would diverge. Even though the sequence didn't, the series will diverge because we're adding it up. If we look at the next sequence that we did, we could pick one of our examples. So say, let's do n equals 1 to infinity. Let's do the 1 over 3 to the n. So if we did this as a series and added it up, 1/3, 1/9. So all I'm doing is plugging in numbers for n. 1 over 27, 1 over 81, so etc. Keep adding it up. Those numbers are going to get super tiny. So in some cases, this one is the odd one. In a case like this, where we are approaching 0, this type of series might converge or it might diverge. It just depends on the series in this case. For this one specifically, these are getting small very quickly. So this one, it will converge to 0. But that is not always the case when it's got a horizontal asymptote of 0. Finally, if we look at the third sequence, we do the summation of the 3n plus 2. If you plug in n is for 1, you're going to get 5. 2 for n, 8. It's going to keep getting bigger and bigger and bigger. So this series will diverge. I should have said this earlier, but at any point if you're confused, please raise your hand and Ms. Wong can stop the video and you could ask questions. So a conclusion we can make based off of this. A series will diverge if it's sequence. So keep in mind sequences and series are different. So series, we're adding things up. Sequence is the pattern. So the series will diverge if its sequence diverges, or if that sequence converges to a non-zero number. Another conclusion, if its sequence, so a pattern, converges to 0, then its series, so when we're adding it up, is sometimes going to converge. But sometimes it won't. And it won't always converge to 0, where like the sequence should be converging to 0, the series will end up sometimes converging to 0, sometimes converging to something else. So at this point, I want the juniors to add up the first 10 terms of A, and I want the seniors to add up the first 10 terms of B, and then talk as a class and determine what conclusions you have. So please pause the video now. now that you have done this, actually let's stay on this slide. So hopefully when you added up the first 10 terms of this, it should have come up with something close to 2.93. And for this one, if you add up all the terms, you hopefully got something like 1.55. And let's actually look at the next slide a little bit. So notice, say this is 10. So if you kept adding these up, this is going to diverge. The reason it's diverging is because the numbers are not getting small quickly enough. So this one diverges because this 1 over 10 is not small enough as we go to turn this into 0. However, on the second one, once you add these up, you're going to end up with 1 over 100 as your 10th term. This one is getting small quickly enough, so this one is going to converge. We can talk more details on that later, but basically sometimes it's going to diverge, sometimes it converges. What you're looking for is whether it converges quickly enough. So is it getting close to 0 fast enough as all these fractions? How about, will an infinite arithmetic series ever converge? So arithmetic means we're adding the same thing every time. So if we keep adding the same thing every time, that's never going to convert. It's going to keep getting bigger. So you will never get close to 0. All right, so going back to day 1, will this series converge or diverge? So we looked at this series on day 1 and we noticed that we're multiplying by 1/2 each time. So my common ratio is 1/2. So last time we talked about the limit as n goes to 0, or n goes to infinity, of that geometric series equation that we have, which is a1 times 1 minus r to the n all over 1 minus r. So that's a geometric series. So what we talked about was as n gets bigger and bigger and bigger, this Rn, if R, RR is a fraction. So if we plugged in a 1/2 here, and we kept making the exponent bigger and bigger and bigger, that's getting really close to 0. So 1 minus 0 would just be 1. So a1 times 1 is just going to be a1 over 1 minus r. So we did this last class. So if we plug these numbers in, my 1 is my a1, so we'll have 1 over 1 minus the rate. So that's 1 over 1/2. So this is going to converge to 2. Remember, we also did that drawing last class, where if we start with 1, and then we want to add on the next term. So if we add on the next term, that's 1/2. Then we're adding on 1/4. Then we keep going to 1/8. And it's going to keep getting smaller and smaller, but it's never going to break out of these boxes. So in the end, we have one box plus another whole box. So that's going to give us 2 boxes, which matches up with this 2 as our answer. So a conclusion to this. When does an infinite geometric series converge? So if you notice something about R here is between 0 and 1. So R is a fraction, and that's important. So our conclusion is if R is between -1 and 1, so it could be a negative fraction. Or we could also say that the absolute value of R is less than 1. That's when a series is going to converge. My timer is going to run out, so I'm going to start a new video. So please stop the video and start the next one.